So we've been working with solutions to the time-independent Schrödinger equation for the infinite square well potential, the particle in a box case. How do these things actually work, though? In order to give you guys a better feel for what the solutions actually look like and how they behave, I'd like to do some examples and use a simulation tool to show you what the time evolution of the Schrödinger equation in this potential actually looks like. So, the general procedure that we've followed or will be following in this lecture is once we've solved the time-independent Schrödinger equation, we get the form of the stationary states. Knowing the boundary conditions, we get the actual stationary states, the stationary state wave functions and their energies. These can then be normalized to get true stationary state wave functions that we can actually use. These stationary state wave functions will, for the most part, form an orthonormal set, psi sub n of x. We can add the time part, knowing the time-dependent Schrödinger equation, or the time part that we got when we separated variables in the time-dependent Schrödinger equation. We can then express our initial conditions as a sum of these stationary state wave functions and use this sum then to determine the behavior of the system. So what does that actually look like in the real world? Not like very much, unfortunately, because the infinite square well potential is not very realistic, but a lot of the features that we'll see in this sort of potential will appear in more realistic potentials as well. So this is our example. These are our stationary state wave functions. This is what we got from the solution to the time-independent Schrödinger equation. This was the form of the stationary states, these were the energies, and then this was the normalized solution with the time dependence added back on, since the time dependence is basically trivial. The initial conditions that I'd like to consider in this lecture are the wave function evaluated at 0 is either 0 if you're outside the, this should be A. If you're outside the domain, you're 0. If you're inside the domain, you have this properly normalized wave function. We have an absolute value in this, which means this is a little difficult to work with. But what the plot actually looks like, if I draw a coordinate system here, going from 0 to A, is this. It's just a tent, a properly built tent with straight walls going up to a nice peak in the middle. Our general procedure suggests that we express this initial condition in terms of these stationary states with their time dependence, and that will tell us everything we need to know. One thing that will make this a little easier to work with is getting rid of the absolute values we have here. So let's express psi of x time t equals 0 as a three-part function. First, we have root 3 over a 1 minus. Now what we should substitute in here is what we get if, say, 0 is less than x is less than a over 2. Sort of the first half interval going out to a over 2 here. In this case, we have something sloping upwards, which is going to end up, in this context, being 1 minus a over 2 minus x over a over 2. So, to say another word or two about that, if x is less than a over 2, this quantity here will be negative. So I can get rid of the absolute value if I know that this quantity in the numerator is positive. So I multiply the quantity in the numerator by a minus sign, which I can express more easily just by writing it as a over 2 minus x. A over 2 minus x. That will then ensure that this term here is positive for x's in this range. 1 minus that is then this term in our wave function. For the other half of the range, root 3 over a 1 minus something, and this is now from a over 2 is less than x is less than a, the second half of the interval. For the second half of the interval, x is larger than a over 2, so x minus a over 2 is positive. So I can take care of this absolute value just by leaving it as x minus a over 2. I don't need to worry about the absolute value in this range. So this is x minus a over 2 all over a over 2. And of course, if we're outside that, we get 0. This technique of splitting up absolute values into separate ranges makes the integrals a little easier to express and a little easier to think about. So that is our initial conditions. How can we express these initial conditions as a sum of stationary state wave functions evaluated at time t equals 0? This is where Fourier's trick comes in. If I want to express my initial conditions as a sum of stationary state wave functions, I know I can use this sort of an expression. This is now my initial conditions, and my stationary state wave functions are being left multiplied, complex conjugated, integrated over the domain, and that gives us our constants, C sub n, that go in this expression for the initial conditions in terms of the stationary state wave functions. The notation here is that if psi appears without a subscript, that's our initial condition, that's our actual wave function, and if psi appears with a subscript, it's a stationary state wave function. So what does this actually look like? Well, we know what these functions are. First of all, we know that this function, which has an absolute value in it, is best expressed if we split it up in two. So we're going to split this integral up into one going from 0 to a over 2 and one going from 0 to a. So let's do that. We have c sub n equals the integral from 0 to a over 2 of our normalized stationary state wave function, which is root 2 over a times the sine of n pi x over a. That's this psi sub n star, evaluated at time t equals 0. I'm ignoring time for now, so even if I had my time parts in there, I would be evaluating e to the 0, where time is 0. So I would get 1 from those parts. Then you have psi, our initial conditions, and our initial conditions for the first half of our interval was root 3 over a, 1 minus a over 2 minus x over a over 2. And I'm integrating that dx. The second half of my integral from a over 2 to a, looks much the same. Root 2 over a sine n pi x over a. That part doesn't change. The only part that changes is the fact that we're dealing with the second half of the interval, so the absolute value gives me a minus sign up here more or less. Root 3 over a, 1 minus x minus a over 2 over a over 2 dx. So substitute in for n and do the integrals. This, as you can imagine, is kind of a pain in the butt. So what I'd like to do at this point is give you a demonstration of one way that you can do these integrals without really having to think all that hard. And that's doing them on the computer. You can of course use Wolfram Alpha to do these. You can of course use Mathematica. But the tool that I would like to demonstrate is called Sage. Sage is different than Wolfram Alpha and Mathematica in that Sage is entirely open source and it's entirely freely available. You can download a copy, install it on your computer, and work with it whenever you want. It's a very powerful piece of software. Unfortunately, it's not as good as the commercial alternatives, of course, but it can potentially save you a couple $100. The interface to this software that I'm using is their notebook webpage. So you can use your Google account to log into this notebook page, and then you have access to this sort of an interface. So if I scroll down a little bit here, I'm going to start defining the problem. A, here, that's our domain. Our domain goes from 0 to a. H bar, I'm defining to be equal to 1, since that number is a whole lot more convenient than 10 to the minus 31st. N, x, and t, those are just variables, and I'm defining them as variables given by these strings, n, x, and t. Now we get into the physics. The energy, that's a function of what index you have, what your which particular stationary state you're talking about. This would be psi sub n. This would be E sub n. E sub n is equal to n squared pi squared h bar squared over 2ma squared. That's an equation that we've derived. Psi, of x and t, psi sub n of x and t in particular, is given by this. It's square root of 2 over a times this sine function times this complex exponential, which now uses the energy, which I just defined here. Psi star is the complex conjugate of psi, which I've just done by hand by removing the minus sign here. More or less just a copy-paste. G of x is what I've defined the initial conditions to be, which is square root of 3 over a times this 1 minus absolute value expression. And c sub n here, that's the integral of g of x times psi from 0 to a over 2 plus g of x times psi going from a over 2 to a. That's all well and good. Now I've left off the psi stars, but since I'm evaluating at time t equals 0, it doesn't matter. Psi is equal to psi star at t equals 0. I did have to split up the integral from 0 to a over 2 and a over 2 to a, because otherwise Sage got a little too complicated in terms of what it thought the integral should be. But given all this, I can plot, for instance, g, and if I click evaluate here, momentarily a plot appears. This is the plot of g of x as a function of x. Now I defined a to be equal to 1, so we're just going from 0 to 1. This is that tent function I mentioned. If I scroll down a little bit, we can evaluate c of n. This is what you would get if you plugged into that integral that I just wrote on the last slide. You can make a list evaluating c of n for x going from 1 to 10, and this is what you get. You get these sorts of expressions. 4 times square root of 6 over pi squared, or minus 4 root 6 over pi squared divided by 9, 4 root 6 over pi squared over 25, 4 root 6 over pi squared over 49. You can see the sort of pattern that we're working with. Some number divided by an odd number raised to the nth power, or squared. We can approximate these things just to get a feel for what the numbers are actually like. And we have 0.99 minus 0.11 plus 0.039, etc. Moving on down. So that's the sort of thing that we can do relatively easily with Sage. Get these types of integral expressions and their values. You can see I've done more with this Sage notebook, and we'll come back to it in a moment. But for now, these are the sorts of expressions that you get for c sub n. So our demo with Sage tells us c sub n equals some messy expression. And it can evaluate that messy expression and tell us what we need to know. Now, the actual form of the evaluated c sub n was not actually all that complicated. And if we truncate our sum, instead of summing from, now this is expressing psi of x t, our wave function, as an infinite sum, n equals 1 to infinity, of c sub n psi sub n of x and t. If I truncate this sum at, say, n equals 3, I'll just have a term from psi 1 and psi 3. Recall back from the Sage results that psi 2, the coefficient of psi 2, c sub 2, was equal to 0. So let's find the expectation of x squared. Knowing the form of these functions, and now knowing the values of these c sub n from Sage, you can write out what x squared should be. This is the expected value of x squared, and it's going to be an integral of these numbers, 4 root 6 over pi squared times psi 1, which was root 2 over a sine, not n, since we're just dealing with psi 1 now, we have pi x over a. We have to include the time dependence now, since I'm looking for the expected value of x squared as a function of time now. And we have e to the, where'd it go, minus I times pi squared h bar squared t over 2ma squared, all divided by h bar, or I could just cancel out one of the h bars here. That's our first term, in our first term of our expression. The next term, we have 4 root 6 over 9 pi squared from this coefficient. Now psi 3 is root 2 over a sine of 3 pi x over a times, again, complex exponential, e to the minus I pi squared h bar squared t over 9 pi squared h bar squared t over 2ma squared, all divided by h bar. Now, what is this? This whole thing needs to be complex conjugated, because this is psi star. What's next? Well, I need to multiply this by x squared, and I need to multiply that by the same sort of thing, e to the plus this minus same sort of thing, e to the plus this. So this is the term in orange brackets here is psi star. This is our x. The term in blue brackets here is our psi. So we're just using the same sort of expression, only you can only see just how messy it is. This is the integral of psi star x squared psi. This is psi star, this is x squared, and this stuff is psi. We have to integrate all of this dx from 0 to a. This is pretty messy as well. Messy, but doable. Now, since I was working with Sage anyway, I thought, let's see how the time dependence in this expression plays out in Sage. So, going back to Sage, we know these c sub n's, these are the c sub n's that I chose for c sub 1 and c sub 3. And c sub n of x gives me some digits. Or, sorry, c sub n evaluated gave me these numbers in just in decimal form. Now I can use these c sub n's to express that test function where I truncated my sum at psi sub 3. So this is our test function. If you evaluate it, it's a lot more simple when you plug in the numbers, sine 3 pi x and sine pi x. When h bar is 1 and a is 1, these expressions are a lot easier to work with, which gives you a feeling for why quantum mechanics often we assign h bar equal to 1. The expected value of x squared here is then the integral of the conjugate of my test function times x squared times my test function, integrated from 0 to a. And Sage can do that integral. It just gives you this. Sage can also plot what you get as a result. Now you notice Sage has left complex exponentials in here. If you take this expression and manually simplify it, you can turn this into something with just a cosine. There is no complex part to this expression. But Sage isn't smart enough to do that numerically, so I have to take the absolute value of this expression to make the complex parts, the tiny, tiny complex parts, go away. And if I plot it over some reasonable range, this is what it looks like. It's a sinusoid, or a cosinusoid actually. And what we're looking at here on the y-axis is the expected value of x squared. This is related to the variance in x. So it's a measure of more or less the uncertainty in position. So our uncertainty in position is oscillating with time. What does this actually look like in the context of the wave function? Well, the wave function itself is going to be a sum, c sub 1 times psi 1, c sub 3 times psi 3, c sub 5 times psi 5, c sub 7 times psi 7, etc. I can do that in general by making this definition of a function where I just add up all of the c sub n's and all the psi sub n's for n in some range. F of x, if I go out to 7, looks like this. You can get a feel for what it would look like if I added more terms as well. Now the plot that I'm showing you here is a combination of 4 things. First, it's the initial conditions shown in red. That's the curve that's underneath here, the tent. And I'm also showing you this approximate wave function when I truncate the sum at 2, just the first term. That's this poor approximation here, smooth curve. the function, if I truncate the approximation at 4, that will include psi1 and psi3. That's this slightly better approximation here, this one. And if I continue all the way up to 20, that's this quite good approximation, the blue curve here, that comes almost all the way up to the peak of the tent. So that's what our approximate wave functions look like, but these are all evaluated at t equals 0. What does that look like, for instance, in terms of the probability density and as a function of time? So let's define the probability density, rho of xt, as the absolute value of our approximate function, and I'll carry the approximation all the way to n equals 20, absolute value squared. And I'm getting the approximate form with this dot n at the end. So this is our approximate form of the probability density calculated with the first 20 stationary state wave functions. This plot then shows you what that time dependence looks like. I'm plotting the probability density at time t equals 0, probability density at time t 0.04, 0.08, 0.12, 0.16. We start with blue, dark blue. That's this sort of peaked curve, which should be more or less what you expect, because we did a problem like this for this sort of wave function in class. Then you go to dark green, which is under here, underneath the yellow. It seems to have lost the peak, and it's spread out slightly. Red is at time 0.08, and if I scroll back up to our uncertainty as a function of time plot, 0.08 is here. So it's pretty close to the maximum uncertainty. You expect the uncertainty, the width, to start decreasing thereafter. If I scroll back down here, this red curve then is more or less as wide as this distribution will ever get. And if we continue on in time, now going to 0.12, that was the orange curve here. And the orange curve is back on top of the green curve. The wave function has effectively gotten narrower again. And if you keep going all the way up to 0.16, you get the cyan curve, the light blue curve, which is more or less back on top of the dark blue curve. So the wave function sort of spilled outwards and then sloshed back inwards. You can sort of imagine this as ripples in a tank of water radiating out and then coming back to the center. This is what the time evolution would look like as calculated in SAGE. You can make definitions of functions like this, you can evaluate them, you can plot them, and you can do all of that relatively easily. Now I'll give you all a handout of this worksheet so that you get a feel for the syntax. If you're interested in learning more about SAGE, please ask me some questions. I think SAGE is a great tool, and I think it has a promising future, especially in education like this. For students, the fact that this is free is a big deal. So that's what the time variability looks like. We had our wave function, which started out sort of sharply peaked, our probability density, rho of x, which I should actually write as rho of x and t, which sort of got wider and then sloshed back in. So we sort of had this outwards motion followed by inwards motion, where our expectation of x squared, related to our uncertainty, oscillated. Oh, sorry. It didn't oscillate about x equals 0. It oscillated about some larger value. Sorry, it didn't oscillate about 0. It oscillated about some larger value. So there's some sort of mean uncertainty here. Sometimes you have less uncertainty, sometimes you have more uncertainty. That's the sort of time dependence you get from quantum mechanical systems. To get an even better feel for what the time variability looks like, there's a simulation that I'd like to show you. And this comes from Falstead.com, which, as far as I can tell, is a guy who was sick of not being able to visualize these things, so he wrote a lot of software to help him visualize them. So here's the simulation, and I've simplified the display a little bit to make things easier to understand. These circles on the bottom here, each circle represents a stationary state wave function. And he has gone all the way up to stationary state wave functions that oscillate very rapidly. in this case. But this is our ground state. This is our first excited state, second excited state, third excited state, etc. N equals 1, 2, 3, 4, 5, 6, 7, etc. Now, in each of these circles, there may or may not be a line. The length of the line represents the magnitude of the time part of the evolution of that particular stationary state. And the angle going around the circle here represents the phase as that evolution proceeds. So if I unstop this simulation, you can see this slowly rotating around. You're also probably noticing the color here changing. The color of this represents the phase. The vertical size of this represents the probability density, and the color represents the phase. So it's a representation of where you're likely to find it, and a sort of color-based representation of how quickly it's evolving. The vertical red line here in the center tells you what the expectation value for position is. And in this case, it's right down the middle. If I freeze the simulation and add a second wave function, this is now adding some component of the first excited state. And by moving my mice around here, I can add varying amounts, either adding none or a lot, and I can add it at various phases. I'm going to add a lot of it, an equal amount as the ground state, and I'm going to do it at the same phase. And I'm going to release and let that evolve. So you can see now the probability density is sort of sloshing to the left and sloshing back to the right. And if you look at our amplitude and phases, you can see the ground state is still rotating. The first excited state is rotating, but the first excited state is rotating 4 times faster. So when they align, you have something on the right. When they anti-align, something on the left. They're aligned, they're anti-aligned. And this sloshing back and forth is one way where we can actually get motion out of stationary states. You notice the phase is no longer constant. You have some red parts, some purple parts, and things are sort of moving around in an awkward way. The colors are hard to read, but you know now that the phase of your wave function is no longer going to be constant as a function of position. So those exponential time parts may be giving you a wave function that's purely real here and purely imaginary here, or some combination of purely real and imaginary, some general complex number. And that complex number is not simply e to the I omega t. It's e to the I omega something that's a function of position as well as time. It's complicated. I can, of course, add some more wave functions here, and you get even more complicated sorts of evolution. Our expected value of x is now bouncing around fairly erratically. Our phase is bouncing around even more erratically. But what we're looking at here is just the sum of the first 1, 2, 3, 4, 5, 6 stationary states, each evolving with the same amplitude and different phases. Now I'm going to stop the simulation and clear it now. Another thing I can do with this simulation tool is put a Gaussian into the system. So I'm going to put a Gaussian in here. So this is sort of our initial conditions, and the simulation has automatically figured out, well, I want this much, I want a lot of the ground state, psi 1, a lot of psi 3, a lot of psi 5, a lot of psi 7, a little bit of psi 9, a little bit of psi 11, etc. And if I play this, I'll slow this down a little bit first. If I play this, you see the wave function gets wide, becomes 2, gets narrower again, and sloshes back where it started. If you watch these arrows down here, you can tell when it comes back together, the arrows are all pointing in the same direction, and when it's dispersed, the arrows are sort of pointing in opposite directions. Since our initial conditions were symmetric, there's no reason to expect the expected value to ever be non-zero, ever move away from the center of this well. But as your, say, psi 1, psi 3, psi 5, psi 7, etc., oscillate at their own rates in time, the superposition results in a relatively complicated dynamics for the overall probability density. And of course I can make some ridiculously wacky initial conditions that just sort of oscillate all over the place in a very complicated way. There are a lot of contributions to this wave function now, and no one contribution is particularly winning, but you can occasionally see little flashes of order in the wave function. I highly encourage you to play with these simulations just to get a feel for how time evolution in the Schrödinger equation works. There are a lot more than just the square well here. There's a finite well, harmonic oscillator, a pair of wells. There are lots of things to play with, so you can get a reasonably good feel with how the Schrödinger equation behaves in a variety of physical circumstances. So that's our simulation, and hopefully you have a better feel now for what solutions to the Schrödinger equation actually look like. To check your understanding, explain how these two facts are related. Time variability in quantum mechanics happens at frequencies given by differences of energies, whereas in classical physics you can set the reference level for potential energy to whatever you want, sort of equivalent to saying I'm measuring gravitational potential from ground level versus from the bottom of this well. And that will tell us everything we need to know. One thing that will make this a little easier to work with is getting rid of the absolute values we have here. So let's express psi of x time t equals 0 as a three-part function. First, we have root 3 over a 1 minus. Now what we should substitute in here is what we get if, say, 0 is less than x is less than a over 2. Sort of the first half interval going out to a over 2 here. In this case we have something sloping upwards, which is going to end up in this context being 1 minus a over 2 minus x over a over 2. So to say another word or two about that, if x is less than a over 2, this quantity here will be negative. So I can get rid of the absolute value if I know that this quantity in the numerator is positive. So I multiply the quantity in the numerator by a minus sign, which I can express more easily just by writing it as a over 2 minus x. A over 2 minus x. That will then ensure that this term here is positive for x's in this range. 1 minus that is then this term in our wave function. For the other half of the range, root 3 over a 1 minus something, and this is now from a over 2 is less than x is less than a, the second half of the interval. For the second half of the interval, x is larger than a over 2, so x minus a over 2 is positive. So I can take care of this absolute value just by leaving it as x minus a over 2. I don't need to worry about the absolute value in this range. So this is x minus a over 2 all over a over 2. And of course if we're outside that we get 0. This technique of splitting up absolute values into separate ranges makes the integrals a little easier to express and a little easier to think about. So we've been working with solutions to the time-independent Schrödinger equation for the infinite square well potential, the particle in a box case. How do these things actually work, though? In order to give you guys a better feel for what the solutions actually look like and how they behave, I'd like to do some examples and use a simulation tool to show you what the time evolution of the Schrödinger equation in this potential actually looks like. So, the general procedure that we've followed or will be following in this lecture is once we've solved the time-independent Schrödinger equation, we get the form of the stationary states. Knowing the boundary conditions, we get the actual stationary states, the stationary state wave functions and their energies. These can then be normalized to get true stationary state wave functions that we can actually use. These stationary state wave functions will, for the most part, form an orthonormal set, psi sub n of x. We can add the time part, knowing the time-dependent Schrödinger equation, or the time part that we got when we separated variables in the time-dependent Schrödinger equation. We can then express our initial conditions as a sum of these stationary state wave functions and use this sum then to determine the behavior of the system. So what does that actually look like in the real world? Not like very much, unfortunately, because the infinite square wall potential is not very realistic, but a lot of the features that we'll see in this sort of potential will appear in more realistic potentials as well. So this is our example. These are our stationary state wave functions. This is what we got from the solution to the time-independent Schrödinger equation. This was the form of the stationary states, these were the energies, and then this was the normalized solution with the time dependence added back on, since the time dependence is basically trivial. The initial conditions that I'd like to consider in this lecture are the wave function evaluated at 0 is either 0 if you're outside the, this should be A. If you're outside the domain, you're 0. If you're inside the domain, you have this properly normalized wave function. We have an absolute value in this, which means this is a little difficult to work with. But what the plot actually looks like, if I draw a coordinate system here, going from 0 to A, is this. It's just a tent, a properly built tent with straight walls going up to a nice peak in the middle. Our general procedure suggests that we express this initial condition in terms of these stationary states with their time dependence